Hello, my name is Andrew Dichenko, and today I'll be presenting our work, Whisper-Flamingo, integrating visual features into Whisper for audiovisual speech recognition and translation. This is joint work with the following authors. In recent years, speech recognition has made major advances, and speech recognition models these days are capable of many tasks, including transcribing speech, meaning given audio, output text in the same language corresponding to what's in the audio, and translating speech, meaning given audio, outputting text in a different language. One such model is Whisper from OpenAI. It was trained on a lot of speech recognition data, about 680,000 hours of data, which included transcription and translation data. And it's capable of performing these tasks for about 100 different languages. However, Whisper and many other speech recognition models have a problem that their performance declines in background noise. So shown on the right are Whisper and other models. And as the noise increases, meaning the SNR or signal to noise ratio decreases, the word error rate is increasing, as we can see on the plot. And these higher word error rates are actually worse. Audio-visual speech recognition is a potential solution to this problem. And in audio-visual speech recognition, it combines lip-based video with the audio input. And audio-visual models can be up to 2 to 3 times better than audio-only models in moderate noise, for example, 0 SNR. However, there's a problem. Audio data is actually much more abundant than video data. For example, Whisper was trained on 680,000 hours of audio training data, but AV Hubert, which is a state-of-the-art lip reading model, was only trained on about 1.7 thousand hours of video training data. So we asked the question, how do we improve audiovisual models with this limited amount of video training data? And in this work, our goal is to combine audio and video models. We want to combine the pre-trained audio speech recognition model like Whisper with the strong visual speech recognition model like AV Hubert for audio-visual speech recognition. And we want to use Whisper's strong multilingual capabilities to do both English speech recognition and English to X speech translation, meaning English audio is the input and multilingual text is the output. So for our method, we have several parts, and the first stage is to make Whisper more noise robust. And we do this by fine-tuning the audio-only Whisper model while adding noise to the audio. And the noise includes speech, music, and babble sounds. And in this stage, we fine-tune all of the parameters. In the second stage, we inject the visual features into Whisper. So we freeze the audio-only Whisper model, and we add new trainable cross-attention layers into Whisper's decoder. And the cross-attention layers are attending to visual features from AV Hubert, which we also freeze. And then we train the model on audiovisual inputs. So recently, the DeepMind Flamingo model injected visual features into a text-based language model using gated cross-attention. We were inspired by this, and so we use gated cross-attention to inject visual features from AV Hubert into Whisper's decoder. The gated cross-attention equation is shown below, is actually initialized as the identity function. And that's because the alphas are initialized to 0 and 10h of 0 equals 0. So then it just becomes the identity function. And the model over time learns to attend to the visual features since it adjusts the alpha parameters. So the model transitions from being an audio-only model to an audio-visual model. We also enable English to X speech translation capability by training on English audio paired with English text and translations in 6 languages. And the supported languages become English, Greek, Spanish, French, Italian, Portuguese, and Russian. This is the overall architecture for Whisper-Flamingo. First, we can notice that there's the Whisper audio encoder-decoder architecture, and the majority of the weights are frozen. Then there's the AV Hubert video encoder, which we also freeze. And we introduce the new gated cross-attention layers, and these are the trainable parameters that learn to attend to the visual features from AV Hubert. And we also have the English to X translation tokens. Here we show like the input and output to represent the training. For the experiments, we train on the Mavic dataset, has 433 hours of English video for training, 1 hour for validation, and 1 hour for testing. For the models, we adapt the Whisper small, medium, and large V2 models. And we make Whisper-Flamingo from those models. And the model sizes become larger because of A.V. Hubert's parameters, 325 million parameters, as well as the gated cross-attention layers. So our large model becomes 2.5 billion parameters after adding those. And for the metrics, we use word error rate for English transcription, where lower is better, and blue score for English text translation, where higher is better. For the test scenarios, we test the models on clean audio, which is testing the model on the original audio, and on noisy audio, where we add noise to the original audio. We add babble noise, which was constructed from 30 speakers, and it's added at a signal to noise ratio, SNR, of 0. And the noise is only added to the audio and not the video. First, we show the results for English transcription. Reminder, it's word error rate, so lower is better. And first, here's OpenAI's Whisper without any fine tuning. And we can see that the performance declines significantly in noise, going from 2.1 to 20.8. Next, we have our fine-tuned Whisper, and fine-tuning it can help significantly in noise. We reduce the word error rate from 20.8 to 11.7. The clean word error rate actually gets slightly worse, but it's around the same, 2.1 versus 2.3. Then we have our audiovisual Whisper-Flamingo, and this model performs the best in noise, gets a word error rate of 5.6, which is much better than the 11.7 from just the audio-only model that we fine-tuned. And the clean word error rate is also improved to 1.5. And comparing with state-of-the-art model A.V. Hubert, we get comparable performance of 5.6 in noisy versus theirs 5.8. So it shows that our model is able to effectively integrate A.V. Hubert into Whisper. Next, we show the results for English text translation, and here's blue score, so higher is better. And this is an average over 6 languages. First off, we have our Whisper that we fine-tuned for this task. And the performance significantly declines in noise. So we can see the blue score drops from 22.7 to 18.6. Next, we have our audiovisual Whisper-Flamingo. And the performance for a clean scenario is actually slightly better, 22.9. It still drops in noise to 20.5, but actually this 20.5 is much better than the 18.6 achieved by the audio-only Whisper model. So it shows that there's a nice benefit of using the visual modality. We can get a much better blue score. And finally, compared to the previous state-of-the-art, our clean performance it's much better, 22.9 versus 21.9. However, our noisy performance is actually slightly worse, 20.5 versus 20.8. For more details, the previous state-of-the-art bilingual A.V. Hubert actually fine-tuned separately per language, and they use a separate model for each target language. However, our Whisper-Flamingo trains on all languages and uses a single model for English transcription and English to X translation into 6 languages. So we think this will be a more scalable approach when we want to train on more languages, say 100 languages. And I'd like to show a quick demo video of Whisper-Flamingo's capabilities.
It's using past experience based on similar situations to try to make meaning. It's using past experience based on similar situations to try to make meaning.
In conclusion, Whisper-Flamingo combines the strengths of Whisper, which is an audio model, and A.V. Hubert, a video model, using gated cross-attention from Flamingo. And audiovisual Whisper-Flamingo significantly outperforms the audio-only Whisper model when tested on noisy audio. And our models perform both English speech recognition and English to X speech translation. And finally, our method is general and can work with better audio and video models in the future. Our paper, code, models, and demo are available on our GitHub. I invite you to try them out. And these were the key references in our work. If you have any questions, please feel free to contact me at my email. Thank you very much for watching.